All right, good morning, everyone. Can someone confirm that you can hear me?
Yes, sir, we can hear you.
All right, thank you very much. All right, we will continue where we started last week. Apologies for starting very, very late. I may at some point need to jump out, but let's see as things go. Last week we started looking at shaft design, and we looked at the design calculations for shafts that are subjected to torsional moments only, and then we took an example or two examples, and then we looked at shafts or axles, which are basically shaft-like elements that are subjected to bending moments only. And we were able to, we started one example, which we didn't finish. And so we will continue from where we stopped. I'm trying to see, I'm trying to look for that document where okay. So I think I should give me 1 minute. Let me reshare this. Leave that to a minute. I think that was too much. Better. Okay. Help me confirm when you can see my screen.
We can see the screen.
You can see the screen, sir.
Yes, sir.
Okay. So we had started this already last week, right? And
Yes, sir.
how far did we go? Let me see whether I can find that document. I don't even know where I saved it. Just give me a second. Or perhaps we should use whiteboard. Okay, over there. From your notes, where were we last week?
No, we stopped at example 2.
We didn't start example 3 at all. We started example 3 now, didn't we?
We just explained the process, then you drop the question down before the class ended.
Okay. Okay. Looks like I saved that to the cloud. Let me. Oh, we just start afresh. But I drawn the free body diagram. I think I did. I did draw the free body diagram.
Yes, I did.
So it will save me if I just find that document. So I don't have to start drawing it afresh. But if not, then we'll just go and start afresh. Let's check machine design. Okay, synced. Let me. So after this class, I will send Romanus the slides and then textbooks, machine design by Shigley, and then the one by Gupta and Kurmi, so that you have two sources to look at, and those are the two texts that I actually use. Okay, so system is rebelling with me this morning. I've got too many things open. What's the time? 17. Okay, while I'm trying to drag this up, we can look at the example. It said that a pair of wheels of a railway wagon carries a load of 50 kilonewtons on each axle box. And those axle boxes act at a distance of 100 millimeters outside the wheelbase, right? And we were told that the gauge of, please make sure, Emmanuel, make sure you mute yourself. The gauge of the rails is 1.4 meters. If we're working in millimeters, that translates to 1,400 millimeters, right? And we're asked to find the diameter of the axle between the wheels, okay? If the stress is not to exceed a certain value. Okay, this has come up now. Confirm that you can now see the sheet we were using to work the last time.
We can see.
Yes, sir.
Okay, great. So Okay, there we go. I'm going to find the diameter of the axle between the wheels if the stress is not to exceed 100 megapascals. And there we go. That was the diagram that we had drawn so far to represent the two loads acting. Now, because these loads are acting and their weights, or the loads themselves rather, are transferred to the rail via the wheels, there will be two reactive forces. Now, when you're drawing the free body diagram, you must take into cognizance all the loads that are acting on your body or subsystem, as the case may be, so that your calculation will not predict a wrong thing. Okay, if you use only some of the forces without taking into cognizance all the forces, then there will be a problem. If I hear anybody, I'll just mute you guys permanently. I don't understand why you should unmute yourself when you don't have to. Okay, so what we want to find now is, or what we are saying is that there are reactive forces. Okay, if we will rotate this one, let's flip vertically. So there are reactive forces acting at the wheel. Okay, so, to be too, yeah, perfect. And this acts on both wheels. Oh, I'm tempted to restart my system because this is getting slow. Okay. So these are the two reaction forces, right? Let's name this critical point so that it's easy to deal with, right? So I can name this point here point A. Okay. A little bit bigger. So if we name this point here for easy referencing, right, point A, then we can name this other point here point B. Okay. Name that point B. Now, consequently, the reaction that is at point A, we can name this, we can name it reaction at point A, right? And then similarly, we can name the reaction at point B like so. Okay, so now that we have done that, we now have our complete free body diagram that tells us where forces are acting, all the forces that are significant in this system, where they are acting, and also the dimensioning of the whole system, right? And so we would have gone ahead to find where on this body is the maximum bending moment acting, so that we can take that value and then impute it into this equation, right? Okay. And find the diameter of that axle as is required. Okay. But we don't know all the forces, so we must find the value of RA and the value of RB. And we're going to use our equilibrium Oh, no, they. Can I have you? Sorry, I'm trying to get my cursor to go to the other side so that I don't have to move.
Let me go outside and I wish I can give. Cheers. That is this school year. Yes. I'm not seeing any.
All right, so we are going to apply the equilibrium equations. Let me confirm that you can hear me. Can you all hear me? Can everybody hear me? Oh wow. Okay. Type, because I've unmuted. I've stopped you guys from unmuting yourself. So if you can hear me, just type in the chat. Okay, that's good. Thank you. Thank you very much. Okay, lovely. So get back to my. So we're going to apply the equilibrium equations, and if you remember them, we said that the summation of all the forces acting, right, on that body should be 0. Okay. And the summation of all the forces acting, all the moments that are acting on that body about a given point should also be 0. Okay. So we're going to apply these two equations to determine the values of your reaction forces at point A and at point B. Okay, so we're going to just stick with a simple notation that forces that are acting up are positive, forces that are acting down are negative, okay? And you might want to show that notation like so. You will say positive forces are, upward acting forces are positive, right? Please stop writing on your screen, Joshua. So we can have that as a notation, and then we can also say downward acting forces are what? Are negative. Okay. And in that case, we can now apply this equation that now sums up what we have here. So we sum this, sum this, sum this, and sum this, because 50 kilonewton, the leftmost one, and the rightmost 50 kilonewton are acting downwards. We give them negative signs based on our notation. And because the reactive or the reaction forces at point A and the reaction forces at point B are acting upwards, we give them positive signs. So we might as well start with the positive ones, that RA, and there's no sign in front of it, which means there is a positive sign there, right? Plus RB minus 50 kilonewtons minus 50 kilonewtons, and this should give us what? 100, right? We sorry, did I say 100? I beg your pardon. I don't know where 100 came from. It should give us 0. The equation says 0. Summation of all the forces should give us 0. My brain is running ahead. We could have equally said, to get the same thing, we could have said upward acting forces must equal all the downward acting, right, forces. Okay, so if we went with that, we would have arrived at the same thing, a step ahead of where we are at this point, right? So if that is the case, then we say that the reaction forces at point A plus the reaction forces at point B must equal the forces that are acting downwards, which is 50 plus 50. Okay, so this is simply a step ahead of where we were before. So that is now going to give us, this is where my brain was already running to, RA plus R sub B, beg your pardon, plus R sub B, and that equals 100, right? Now, then we take moments. We take moments about any of these points. You can take moments about any of these points, but to ease your calculation, it's advisable to take moments about one of the points where your unknown forces acts, because moments are products of forces and the perpendicular distance between the line of action of those forces and the point about which you are taking your moment. When a force acts at your point of moment reference, then the moment of that force is 0. So in so doing, we eliminate one of the unknown forces. And so we're left with 1, and it's easy to calculate. So we will take moments either about point A or point B. Any one is fine. It will give you the same thing. You only find the other force. Okay. So let's take moments about point A. If we do that, then we're going to eliminate RA, because the moment of RA about point A is 0, right? Because RA acts exactly at point A. So we will say taking moments about point A, okay? That will give us this. So we're going to take moments, and of course, moments is a product of force times perpendicular distance. So we need to find out what is the distance, what's the moment of the force, 50 kilonewtons about point A. There's going to be 50 kilonewtons times 100 millimeters, okay? And then if we take moments of the force RB about point A, it will be RB times 1,400 millimeters, right? And then we can also take moments of this second 50 kilonewtons about that, and this will be 50 kilonewtons times 1,500. That's the total distance from the line of action of this second 50 kilonewtons and the point at which we are taking our moments. Okay, please do note that very carefully. So we must also now note our notation, and we can say clockwise moments are positive, okay, and anti-clockwise moments are negative. All right, we can have it that should bring this down so that are negative. Okay, or you could as well just simply say clockwise moments must equal anti-clockwise, right, moments. Okay, so in that way you just need to arrange them, but let's use the first one to get our equation. So we'll start with 50, the leftmost 50 kilonewtons, right? If we're taking moments about point A, okay, you're pivoting at point A, this force will cause this body to move in this direction. Now, if we check your watch, this direction is going against how your second hand moves. The second hand of your watch or clock moves like this, okay? Okay, so since this is going this way, it is an anti-clockwise moment. And so it's going to carry a negative sign. Okay, so as I'm starting with that first, it's going to be minus 50, okay, times 100. Okay, and of course, the unit here is going to be kilonewton millimeter. Kilonewton millimeter, because I'm working with that. Okay, so far as I remain consistent with my units, that's fine. So whatever force I get at the end will be in kilonewtons. Okay, so we've gotten that. Now let's check the next force. Again, remember that Ra is going to vanish because it cannot have moments about the point where it's acting. It's of no effect. Okay, what that means is, since that's the point that is pivoted, no matter the value of Ra, this body will not rotate in any direction. It will remain exactly the way it is. Now, but let's look at RB. Let's take moments of RB about point A. Okay, if we pivot this whole system at point A and we apply RB at the point where it's acting, the tendency is for this system to rotate in this direction. Okay, so you can see that this direction again is going against the normal direction that your second hand of your clock or watch goes. So this is also anti-clockwise. All right. So what that means is we are going to have another minus. Okay, this time around it is RB and it is multiplying I'm multiplying it by 1,400 because that is the distance between where am I? Yeah, that's the distance between RB and point A. Then the next force available for us is the second 50 kilonewtons, right? And that acts at a distance of 1,500 millimeters. But when we check the line of action, okay, if we pivot the system at point A, then this force will tend to move this system in this direction, okay, which is the same direction as your second hand of a clock or watch moves. So that is a clockwise direction. And so that value there will be positive. Give me a minute. Are you? There we go. Okay, so let's go back down here. So the next value we're looking for is a plus, and it's plus 50 times what's the value now? 1,500, and all of this should equal 0. So when you look at this, you have an equation with only one unknown that we can easily solve. So let's quickly isolate your RB times 1,400 on one side of the equation. Let's retain it on the left-hand side. Okay, so watch what I'm going to do. I'm going to say this is RB, right? Or since that's multiplying that, we'll say this is 1,400 RB, right? And this equals, this is going to equal 50 times 100 will give you 5,000, right? And then 50 times 1,500 will give you what? What will 50 times 1,500 give you? That should be 75,000, right? 75,000. Please verify those values. You can put it in the comments, okay, so that I can see. 75, oh yeah, 75,000 minus 5,000, right? And this is going to be 1,400 RB will equal 70,000. Okay, so what that simply means then is that RB, if we divide both sides by 1,400, will be 70,000, okay, divided by 1,400. Yeah, and somebody has, Romanus has given us the answer already. Okay, and that is going to give us our RB to be 50. Okay, don't forget the units, 50 kilonewtons. All right, so obviously when you look at our equation, we should have been numbering this equation so we know which one we're dealing with. Okay. When we come back to this equation, if we had called it equation 1, then it's obvious that we can see what value RA will be, since we know RB to be. Can you guys stop interacting with your screen so that we don't have marks all over you? So we have your RB to be 50, and we said if you sum RA and RB, you'll have that, okay? So we come back here, say, it's there. It follows that our RA is 100 minus RB. So I'm going step by step so that you will know how to present this in your exams, right? And that simply means that RA is 100 minus 50, which is 50 kilonewton. Okay. Great. So we have the values of both RA and RB. The next thing we're going to do is to draw the bending moment diagram. Okay. What we're going to do is to identify the critical points in this subsystem, in this system, and then find out what the value of the moment, okay, the moment is at that point, and then we draw. So if we are doing that, we will take a line. Where is my shapes? We will take a line right here, a horizontal line. It has to be horizontal. So 0 there. Okay. And this line here, if we will be, it will represent our bending moment axis. So the value of the bending moment at that point will be 0, right? And the same thing on this side, that the bending moment along this line is also 0. Okay. So this, we'll call it bending moment. So this diagram that we're going to draw here is going to be actually downwards. Okay. So what that means is, so these lines act as scales for us. If you go above the horizontal line, that direction, you are dealing with a positive bending moment. If you come down, you are dealing with a negative bending moment. All right. It just shows the direction of the bending moment and not necessarily the value. Okay. When we're dealing with the value, we look at the absolute value to know the magnitude, which one is the highest. So what we're going to do there's a critical point there. There's another critical point here. So I'm going to, where's my line? I'm going to place another line at. So all the points where your forces are acting, those are your critical points. All the points where your forces are acting are your critical points. They will automatically have higher values, right, of shear forces and bending moments than all the other points in the shaft. So my critical points are the points where these vertical lines have passed through. So what I want to do is to find okay, what I want to do is to find the value of the bending moments of each of these points. Okay, now follow me carefully. You usually would start from the left-hand side of a subsystem and walk towards the right. You can also start from the right-hand side. In fact, by the time I do 1, 2, to get these other ones, I move to my right-hand side. It doesn't matter which direction you use, you will get the same thing. Now, follow me to get what I'm saying. Watch carefully. I want to find the total moments that are acting at the point where this 50 kilonewtons is acting. Okay. Now, if I'm coming from my left-hand side, I look on the left-hand side of this force. Are there any forces? I'm going to unmute you guys now so that you can talk, because this is very important. So if you want to speak, please unmute yourself. If you are not speaking, please mute yourself. Is that okay? So on the left-hand side of the 50 kilonewton, is there any force there? Do you find any force acting on the left-hand side of that leftmost 50 kilonewtons?
There's no force acting on the left side.
Good. There's no force acting. And so the moments about this first point where I am is 0. There's no force. Now, if we look from the right-hand side, and I will do this only once, so you see that it will always give you the same thing. If we look on the right-hand side, okay, we have 3 forces acting. One force, the rightmost 50 kilonewton, is going to cause this system to move in a clockwise direction, right? Then RA and RB, which both have values of 50 kilonewtons each, right? They are working in the opposite direction. Okay. So the moment that this force creates about the first point that I'm dealing with is going to be 50 times 1,500. And it gave us 75,000, right? We're going to subtract from that value, because that moment is clockwise. We're going to subtract from that value the moments of this force and this force. Okay. So let's subtract. Let's do the math. RB is 50 kilonewtons, right? If you subtract RB, if you multiply RB, which is 50 kilonewtons, by 1,400, 50 times 1,400, what will you have? You will have 70,000, okay, kilonewton millimeters. So we already have a 75,000 kilonewtons millimeters minus 70,000 kilonewtons millimeter. Then here, RA is also 50, okay? 50 times, what's the distance? 100. That will give you what? 5,000, okay? So 75,000 minus 70,000 minus 5,000 will give you what?
0.
To give you 0, right? So it doesn't matter the direction you come from. At every critical point, right? If you are coming from the right-hand side, or if you decide to come from the left-hand side, you will have the same value of the moments acting at that point. So just to make our work easier, we deal with the side that has the lesser amount of forces. So again, at this critical point here, the leftmost 50 kilonewton, right? If you look at its left-hand side, there is no force. If you look at the right-hand side, there are 3 forces. I'd rather work with the left-hand side because I know that there is 0. And so what I will do is to put a dot, a small dot. I'm going to just use small dot. Let's have the same value and let's make it black. I'm going to keep, it's so small, it doesn't want me to hold it. Let's make it a little bit bigger so that I can. Okay. So let's place that dot there at the 0 point, right? To signify that the value of the moments about this point is what? Is 0. So it's sitting on this line that we've drawn. Then we take the next critical point, which is point A, and we find the value of the moment about that point. Okay, so you look on both sides. From the left-hand side, we have 1 force. On the right-hand side, we have 2 forces. So I work with the left-hand side, right? So 50 kilonewtons times the distance between these two will give me the value, right? And if I'm taking moments about point A, as we did before, this 50 kilonewton tends to act in an anti-clockwise direction. It causes a moment that is anti-clockwise in nature. Okay, so 50 kilonewtons times that will give us 5,000 kilonewton millimeters. You can decide to change that into meters as the case may be, but I will leave it at that point, right? So I'm going to copy that and paste. Remember that it's going anti-clockwise, and so its direction will be negative. So I'm going to go below this line. I'm going to find somewhere below this line as my 50 kilonewton, right? Point. Okay. So I need a label there to show me. These labels here tell me that the point where I'm at is 0 kilonewton millimeter, right? So I need another label here to tell me that at this line where I currently am, the value here is 5,000 kilonewton millimeter. Okay, and to make that longer. Okay. And if you want, you can say 5 times 10 raised to power 3 kilonewton millimeter, and you can easily convert that to 5 times 10 raised to power minus 6 Newton millimeter. Okay, it's just maths. Now it's a negative value, so that we have to take into cognizance the negative sign because it's below the line. If this were a clockwise moment, then it would be above the line. All right, then we move to the next critical point, which is point B. Okay, I look at the left-hand side. There are 2 forces coming this way. Okay, and I look at the right-hand side, it's only 1 force. So I will decide to go with the right-hand side. So again, here we have 50 kilonewtons, and it is at a distance of 100 millimeters from that point. Okay, if we multiply that, you will still find 5,000. The question is, in what direction is this going? Okay, in what direction is this going? So when you look at it, and you put you are fixing it at point B. Okay, it looks as though, and this is where we have to be very, very, very careful. At point B, with respect to this force, it looks as though this thing is going in a clockwise direction. Okay, but for consistency, the reason why I'm deciding to choose the right-hand side is only because it makes my calculation easier. if you want to know the actual value of the actual signage, consider the forces on your left-hand side. Okay? Please follow me very, very carefully. Let's test this to see if we'll have the same thing. All right? If I were walking on the left-hand, from the left-hand side, since I started working from the left-hand side and I'm coming, this is for sign. Please follow me carefully. 50 kilonewtons, the leftmost 50 kilonewtons is going to have a moment of 50 kN times 1,500. And the direction is anti-clockwise. Okay? Then RA, which has a value of 50 kilonewtons, is itself clockwise, right? However, its moment about point B is 50 kilonewtons times 1,400. If we were going to do the math from the left-hand side, the bigger force is going in an anti-clockwise direction. The smaller force is going in a clockwise direction. Anti-clockwise is negative. Clockwise is positive. Since the negative number is bigger than the positive one, the overall value you have will be negative. And the reason why that balances this one, because we said that this system is in equilibrium. So if this clockwise moment this side is negative, the one that is coming on the right-hand side will be positive. Okay? But for value, to ease my calculation, so I went to my right. But the sign of the moment at point B is negative. Please note that it's negative because our convention is we started from the left-hand side and we're coming towards the right-hand side. Listen to me carefully, if you are started from the right-hand side and you are moving towards your left-hand side, and for ease of calculations, you started with this one, then you move to that, and then you had to switch to the other side because, it's easier to calculate from the left-hand side at this point, at point A. That's if you started from the right-hand side. Then you must maintain for consistency, you must maintain the signage, the direction you started with your right-hand side. Okay? If all of this is confusing for you, just start from the left-hand side and go meticulously until you get to just do all the laborious calculations. In that way, you will not confuse your signs and all of that, but you have longer calculations. But if you want to shorten your calculation, okay, I started with, from my left-hand side, moving towards my right. That's the standard way. I started with the leftmost 50 kilonewtons. There was no force acting on the left-hand side. I gave it a value of 0. When I came to the point A, the one force was acting on the left-hand side. You multiply that by 100, you have your value 5,000 kilonewton millimeters, but it was anti-clockwise. Then we move to point B. Okay, then now we have two forces on the left-hand side. For consistency, you will maintain. But I said, instead of using those two forces to calculate, I'm going to use the one on the right-hand side. It's just one. That will give me my value of 50 kilonewton millimeter. You will get that same value if you do this first force minus that. The problem now is, what is the correct sign at this point? You need to come back to your values on your forces on the left-hand side. The bigger one, and it's bigger not because of the value of the force. What we're looking at is the moment. Both of these forces have values of 50 kilonewtons, but this one is the leftmost force. Okay, so when we multiply that 50 kilonewtons by 1,500, that's what makes it bigger. It's not because the distance is bigger, that's why it's bigger. No, it's a product of the force. If this force were, let's say, 100, if this force were 100 kilonewtons, then this moment here is bigger than that one. And since this will now be clockwise, positive, and that is anti-clockwise, negative, if RA were 100, then this moment, the moment caused by that force, is the bigger one, and your resulting sign here will be positive. So don't confuse our saying which is bigger just by distance or by the value of the forces themselves. No, it's the product. You have to multiply them first to determine which is bigger. So 50 times 1,500 give us 75,000. 50 times 1,400 give us, I'm in the mixing, go and ask mommy. Will give us 70,000. And you're comparing both of them, which is bigger. 75,000 is bigger and has a negative sign. So the value at this point is exactly what you have here. So I'm just going to copy that and I'm going to move it to a point that should be horizontal. Okay. I will ask Auntie Priscilla. Okay. And then the same thing will happen here. Okay, when you get to this point, you will have a 0 because at this point here, there's no force to the right side of it. So the moment about this point is 0. Okay. So usually these things close up as you go that way. So we now need to, it's a bending moment diagram. Okay. It's a bending moment diagram. So we need to close up the shape. It's the area under that gives us an idea. This is 0 kilonewton millimeters, right? So we're going to pick a line. We're going to draw from there to here, right? And then from here to here, it should be horizontal. That is obviously not horizontal, so I'm going to make it horizontal 0. Then I'm going to pick all right, then we pick a where is it now? Where is my, okay. We are, okay. So this area under here, okay. Oh, usually I don't have time to shade, but when you are drawing it in your exam or in your own book, you will need to shade that area there, right? And that gives you the bending moment diagram. So when you look at this, because this line is horizontal, we know that the value of this force at this point, I mean the value of the moment, not force, value of the moment at this point is the same as the value of the moment at that point. I will not go into the shapes because these are point forces, all right? These all have straight lines that connect the values at the critical points. They're all straight lines. If this were a distributed load, then it will not be a straight line. You would have a parabolic shape, a curve that shows how that force varies as you go along. Okay. But what that means is that when you look at this shape, from this first critical point here, okay, from the tip of your shaft, as you come along the way up on this point, all the moments in that in every segment of this shaft up until this point is all 0 kilonewtons. Then from this point, the value begins to rise steadily. Okay, if you plot this on a graph, you can tell what the value of the bending moment is at every point between 50 kilonewtons and point A. But at point A, the value of the moment, the bending moment in the shaft will be 50 kilonewtons millimeters. Okay, and that value stays the same. So from point A, as you travel along that shaft until you get to point B, every segment of that shaft between point A and point B experience a bending moment of 50 kilonewton millimeter. Okay, then when you get to point B and you begin to travel towards the right-hand side 50 kilonewtons, the value of your bending moment begins to decrease again until it becomes zero. That's simply what the bending moment diagram is telling us. So all we did this for was to determine, so what then is the maximum value of the bending moment that is acting in this shaft? That's the question. So what's the answer? What's the maximum bending moment acting in that shaft?
5,000 kilonewton meter.
5,000
kilonewton millimeter.
Millimeter. Thank you very much. Okay, that's the value. So we now know that so far as this shaft is concerned, we've done the bending moment diagram. We can say that the maximum bending moment acting in the shaft is, right, M equals, now again, you don't need to take the minus. We're not concerned about the direction. We are only concerned about the magnitude. Okay? The magnitude. So if you want, you can take the modulus of that value. And we say that's 5,000 kilonewton millimeter, which we can express as 5 million newton millimeter, or 5 times 10 raised to the power 6 newton millimeter, right? So we're now going to pick one of the equations we developed last week, this one. So of course we have copy. We have two of these equations. One of them is a solid shaft, one is a hollow shaft. This question did not tell us what kind of shaft, but common sense should tell us that it's going to be a solid shaft. You do not use hollow shafts on railway. But since it was not told us, we can include our assumption. We did not even say what we were given in this question before we started drawing. Okay, so let's come back here and let's do what we're given. We're given that the what's it called now? The bending moment so our bending moment underscore B is 100 megapascals. And remember that megapascals is the same thing as what? What's megapascals? Newton per millimeter square, right? Oh, no, that's not what I want. Newton per millimeter square, yeah. Okay, so that's what we're giving. On all the other dimensions, the 50 kilonewton, the 100 millimeters, the 1.4 meters, we have represented that on our free body diagram. So we have taken into cognizance those values. Now, but we need to assume, okay, assumption is that the shaft is what? Is a solid, it's a solid shaft. With that assumption, we will now, now this needs to come down completely so that, well, I'm not going to give you this. Am I going to give you this thing? No. since you have the slide, so you understood the principle. Where am I now? So that's the maximum bending moment. So using the equation, this, right? We don't need you to be highlighted. Using that equation, we can say that our D is the cube root, okay, is the cube root of two things. We are going to multiply 32 by the maximum bending moment and divide that by pi, and the maximum allowable bending moments in the structure. Okay, we know the value of sigma B, which is 100 megapascals. We had that there, and we have now found the maximum bending moment acting in the shaft. So now we know that value, we know this value. This is a number, this is a number. We can evaluate what D is. So this is simply, so we can still write in this equation that this equals the cube root of, what's the value here? 5 times 10 raised to the power 6, right? Newton millimeter, okay? And this guy here, the value for this guy is 100, and it's Newton per millimeter squared. So Newton we cancel, and you'll be left with millimeter cubed, and all of that will leave your value in millimeters. So I expect that somebody should have punched their calculator to tell us what D will be. What's the answer for D? What's the answer for D?
7.986, sir.
7 points. Are you sure?
It's 79.86 millimeter.
That's better. 79.86 millimeters. Okay. So, based on the standard shaft sizes, what size should we select? Based on standard shaft sizes, what size will we select?
80, sir.
80 millimeters, right? Okay. An axle size of 80 millimeters is selected according to the standard shaft sizes. And that's all they asked us to find. We should find the diameter of the axle between the wheels if stress is not to exceed that. And so we say, or we can write that the diameter of the axle, right, between the wheels should be 80 millimeters, okay, to ensure the moments or the stresses do not exceed what? 100 megapascals. Great. So have you followed to that point?
Yes, sir.
Any questions? Now note that we have to only do the bending moment diagram thing when we're dealing with bending moments in the shaft. And the whole essence is so that we can find this value. We can know what the maximum bending moment will be. So when your question is given to you, you will need to first, the goal is to find that, because when we find this, we can plug it into this equation and find the value of D, either this or this, depending on whether the shaft is hollow or whether it is solid, right? And so you look at the question to find the maximum bending moment, you must know all the forces acting. And that's what takes us to begin to use the equilibrium equations. That's just to help us find all the forces. If they had told us the values of all these forces, then we would not need to go this route of trying to find the unknown forces. But if you are not told, then you must calculate first to find your unknown forces. When you find your unknown forces, then you now calculate to know what the maximum bending moment will be. Okay? And then you take that value and apply it in the equation that we developed to now calculate the diameter of the shaft. Is that clear? Okay. So we are going to now switch back to... Please mute yourself if you are not saying something that is relevant to us. So finish all of that. Now we are going to move to shafts that are subjected to combined twisting and bending moments. Okay, so this is now becoming more realistic. You would really not find, except the weights of your transmission elements are really negligible, right? But it's rare to find such cases. So most or oftentimes, what's the English now? I've forgotten what I wanted to say now. The point is, you will find more cases like this where your bending moment...
Sir, our network got interrupted at some point.
Your network or my own? Whose network got interrupted?
Yeah,
Is it mine or yours?
It was your network.
Their own, right? Okay.
Yes, sir, they work
I have no control over your own network. If it's mine that is...
Sir, continue, sir, continue.
Okay. All right. So we said that the most shafts that you find in operation are closer to a case where you have both twisting moments, so they are transmitting power, they are spinning, and at the same time, because of the things mounted on them, they are subjected to bending moments also at the same time. Okay, and so we need to take into account both the stresses developed by the weights hanging on the shaft and the spinning of the shaft, the torsional moment, or the torque that the shaft transmits. Okay. And there are several theories that have been developed to account for the failure of shafts, okay, as a result of these two stresses. If you look at Shigley, you'll find very complex equations, and so we're still going to stick with these guys for now, right? So two theories that are used that we will employ in this class are the maximum shear stress theory, or what is called the Guest's theory, which is primarily applied to materials that are ductile in nature. Okay, so they have a measure of so if you apply tensile forces to them, they stretch first before they break. And then you have brittle materials that they break very easily, okay? So when you apply tensile stresses or forces to them, they don't stretch. They just fracture immediately. They don't have an elastic region. Okay. So we have now the maximum normal stress theory, or what we call the Rankine's theory. The maximum shear stress is called the Guest's theory, and then the maximum normal stress theory is called the Rankine's theory. And the maximum normal stress is used for brittle materials such as cast iron. So if they tell you the type of material and you know whether the material is brittle or not, then you use either of these, okay, these theories. Otherwise, you will need to apply both theories, okay, and compare the value of the diameter between both of them, and then you choose the bigger diameter. Okay, so let's look at the maximum shear stress theory. Okay, give me a minute. All right. So according to the maximum shear stress theory, right? The maximum shear stress that the shaft experiences, right, can be expressed by this expression, this equation that we have, okay? That the tau max, as the maximum shear stress, equals half the maximum the maximum allowable bending moment in the shaft squared plus 4 times the maximum allowable shear stress. So you see that both of these stresses are playing in this equation. When it was only the torsional moment, we considered only the maximum allowable shear stress in the material, right? And both of these are functions of the material you select. Okay. When we came to axials that were experiencing only bending moments, we had just the maximum allowable bending moments active. But because we are combining both, we say that if we're going according to the maximum shear stress theory, then the maximum shear stress created in this body is going to be a combination of the maximum allowable shear stress and the maximum allowable normal stress, and then the maximum allowable shear stress. And that's the equation there, right? So we take this, if we are using our shear stress theory, we substitute this in, let me go and find that equation, the equation that we had developed for, where am I? The equation that we developed for the maximum bending moment and the maximum shear stress. So if we go to, where is that equation now? I'll get it for you in 2 minutes. There. Okay, where we said that the torque acting, or the torque transmitted by that shaft is expressed as, or it equals pi over 16 times the maximum allowable shear stress, okay, times d cubed. So we're saying that we take the value of tau and input it here, right? At the same time, we do the same thing for the one we developed as the, where are we? This one, okay? And when you combine both of those, I don't have time to be doing proof of formulas for you. You can go and look at it. We arrive at this point. What we do is we make sigma b from equation 14 the subject of formula, and then we substitute it here, And then we make tau the subject of formula from equation 5, and we substitute it here. Okay, you can go and try that out. And then this is what we have. Okay, so when you manipulate the equation, you arrive at this point, okay, where we said that the pi over 16 times tau max times d cube is given as the square root of the maximum bending moment acting in the shaft squared plus the torque to be transmitted in the shaft squared. And we call this expression on the right-hand side the equivalent twisting moment, because this equation looks exactly like the equation in equation 5 that we developed for a shaft that is subjected to only torsional moments, that the torque to be transmitted or the twisting moment to be transmitted is the same as pi over 16 times the maximum allowable shear stress times d cube. But this case, based on the maximum shear stress theory or the guess theory, where we said that, okay, the maximum shear stress developed, if we're going to go according to the shear stress theory, then the maximum shear stress developed in this material is going to be a combination of the maximum, the maximum allowable bending moment and the maximum allowable shear as a bending moment, shears, normal stresses, and the maximum allowable shear stresses, right, combined. And that leads us to this equation that looks similar to where we started from. Just that this time around, this equation on the right-hand side, we call it the equivalent twisting moments, and it's denoted by T sub E. All right? And we define the equivalent twisting moments as that twisting moment that when acting alone has the same effect as the actual twisting moment that is transmitted in the shaft in conjunction with the bending moment, because it's a combination, right? We're combining this and this. We're combining those two. Remember, it's a case where you have both torsional moments and bending moments. And so the equivalent twisting moment is that singular, right, twisting moment that when it's acting alone, it has the same effect as the shear stresses that are developed in the shaft as a result of the twisting, the actual twisting moment that happens there. Okay, so if we limit the maximum shear stress to the allowable shear stress, remember that the maximum shear stress that this thing can take is actually different from the maximum allowable. So if we limit it, then we can express this equation like so. And this is now what we now use when we are dealing with a case where you have combined bending moments and shear stresses, right? This is what we now use, okay? Where we'll have to find the maximum bending moment in the shaft. We'll have to know the torque to be transmitted by the shaft, and then we equate that to what we are very familiar with from the first case. Okay, now this is the maximum shear stress theory. Now, if we are dealing with the maximum normal stress theory or the Rankine's theory, then we say that the maximum normal stress developed in the shaft can be expressed like this. Okay, half this value, okay, plus half the square root of, if you can recognize this was what we used for the maximum shear stress theory, right? This second expression. But for the maximum normal stress, we're including that, okay? Half the maximum allowable bending stresses or normal stresses inside the shaft. Okay? So again, we go and bring the values from the equations that we had developed earlier. We make sigma sub b and tau the subject of formulas from those two equations, and we substitute. And when you manipulate this, you arrive at this equation. Okay. In this case, half bracket open the maximum bending moments in the shaft plus the square root of the maximum bending moment squared plus the torque to be transmitted squared. This whole guy is referred to as the equivalent bending moment. And we define it as that bending moment which, when it's acting alone, has the same effect, the same tensile compressive effect as the actual bending moment that the shaft is experiencing. Okay, of course, he's now combining both what is happening from the transmission of the torque and just the normal ordinary bending moment that the weight of the transmission elements produce on the shaft. Is that okay? And so if we limit the maximum normal stress to just the maximum allowable bending stress, then that equation becomes this. Okay? And you can similarly have the same equation for a hollow shaft just by incorporating that expression as we had developed earlier. Okay? Now note. We always suggest, if you are not sure which of these two theories is to play, because you don't know whether the shaft is the ductile shaft or a what's it called now? Or a brittle shaft, right? Then you use both of these equations separately to calculate the value for the diameter. Okay, if you're using for a hollow shaft, that. If you're using for a solid shaft, this and this. You use both of them to calculate the diameter, and then you select the biggest diameter from the two. Whichever diameter is bigger, is larger, you select that one. All right. So far, these are the equations that we have developed for determining the size of the shaft. When you have only oh my Lord, I was just showing it only on my screen. Anyway, when you have only torsional moments, you assume there is no bending moment. Then the equation you use is this equation that says that the torque developed, or the torque transmitted in the shaft, equals pi over 16 times the maximum allowable shear stress in that material times the diameter that the shaft should be raised to power 3. If it is a hollow shaft, then your d cube becomes the outside diameter cube, bracket open 1 minus k to power 4, where k is the ratio of the inside diameter to the outside diameter of the hollow shaft. Is that okay? And then we also did mention that you can find the torque that is transmitted if you know the power to be transmitted and the speed of the shaft in revolutions per minute, okay, using that expression. If it's a case of a belt and pulley system, and you know the tensions in the tight and slack sides of your belt, then the torque that is transmitted is gotten by that equation. Okay. Then we came to deal with maximum, the case of an axle, okay, a shaft-like entity that is subjected to only bending moments, no torsion. That means it's not spinning, no torque. It's not spinning. It's just stationary, but it is carrying elements that are they themselves spinning or maybe just sitting, right? And we said that you can find the diameter of that shaft through this equation if it's a solid shaft, right? That the maximum bending moment developed in that shaft should equal pi over 32 times the maximum allowable normal stress according to the material of that shaft times the diameter that that shaft should be raised to power 3, right? And if it's a hollow shaft, we just replace that by this. Okay. And then a case where you have combined bending moments and twisting moments, bending moments and torsional moments in a shaft. So the shaft is spinning and it also carries on itself elements that have weights. Okay. Then there are two theories that you could use. You could use the maximum shear stress theory or the Guest theory, okay, which results in this equation that the equivalent twisting moment is given by the square root of the maximum bending moment in the shaft squared plus the maximum torque to be transmitted or twisting moment squared, and that should give us pi over 16 times the maximum allowable shear stress in the material times the diameter raised to power 3. Okay. And if it's a hollow shaft, again, you just replace it by that. And then the second theorem is the maximum normal stress theory or Rankine's theory. Okay. Which says that the maximum or the equivalent bending moment in that material, right, is given by this half what you see here, and that should equal pi over 32 times what you see there. And if it's a hollow shaft, then you replace that T with this one. And we said for the combined case, what we need to do is to calculate both cases. Is that okay? We are going to employ both theories and calculate to find the diameters in both theories. Then whichever one is the bigger value, whichever one is the larger value, we select that as our working diameter. Any questions? We'll take one example. My time will allow me to take only one example and I'll have to run. Any questions? No questions. Okay. So let's look at this example, right? A solid circular shaft. So here we're told the solid shaft, so we don't need to assume anything. A solid circular shaft is subjected to a bending moment of 3,000 Newton meter. They have just done us a whole favor by giving us the bending moment. So we don't need to go and start calculating to find what the maximum bending moment will be, right? They've given us. And a torque of 10,000 Newton meter. 10,000 Newton meter. The shaft is made of 45C8 steel, having an ultimate tensile stress of 700 megapascals and an ultimate shear stress of 500 megapascals. And we are asked to determine the diameter of this shaft if we assume a factor of safety of 6. Okay, so let us go and calculate. Give me a minute. Okay, so we want to do example 4. Example 4. And oh dear me. Unmuted now. Okay. Please help me confirm that you can hear me.
Loud and clear, sir.
Thank you. Thank you. All right. So we said a solid circular shaft is subjected to a bending moment of 3,000 Newton meter and a torque of 10,000 Newton meter. The shaft is made of this kind of steel that has of what? Of 500 megapascals. And we are asked to assume a factor of safety as 6 and to determine that. So what have we been given? What have we been given? We have been given capital M, right? Which is your maximum bending moment acting in the shaft. And we are told that that is 3,000 Newton meter. Okay? 3,000 Newton meter. And then we have also been given the torque. The torque has been given to us as 10,000 Newton meter, right? 10,000 Newton meter. Then we were told that the ultimate tensile stress, that is sigma sub B, right? Ultimate is given as, what's the value? 700 megapascals. 700 megapascals, which will leave that way. That's Newton per millimeter, right? And then I think I should bring you down. Oops, not what I wanted. Better. And then the, what's it called now? Tau. Sorry. Tau ultimate is 500 megapascals. Great. So this is what we've been given. And so we need to find the shaft. We are going to apply two theories. Don't forget, we're going to apply two theories to calculate and find which of these is the biggest. Now, the first theory that we are applying is this, that says that the equivalent twisting moment can be found by this expression, the square root of m squared, which we know, plus t squared, right? And that is the same thing as pi, or that is the same thing as pi divided by 16 times our maximum allowable shear stress times d raised to power 3, right? That's what this thing is. So we can go and find this value separately and then bring it in. So from this expression, we can say that d will be the cube root, d will be the cube root of what's going to be down here? I mean, up here will be 16 times the equivalent value of that divided by pi times what? Times tau. Okay, so that's what we're looking for. Okay, so we check. Do we know TE? We have not been directly given TE, but we know the expression. We can find it. Since we are given M and T, it's easy to find that value, right? Next thing is tau. we are not given tau directly, we are given tau ultimate. I didn't even include my factor of safety. I've also been given a factor of safety of what? Of 6, right? So let's go ahead and find these things. Let's start with what the maximum allowable shear stress, right? I can find that, excuse me, sorry. Okay. So tau can be found by getting the ultimate shear stress and dividing that by the factor of safety. Okay, so this will be, what's the value of the ultimate shear stress? I think it's 500, right? It's 500 megapascals. So 500 megapascals divided by the factor of safety, which is 6, right? And what would that value give us? What's 500 divided by 6?
83.3.
83 point what?
3.3
megapascals. Okay,
megapascals.
thank you very much. So having found that, let's find what our equivalent twisting moments will be. The equivalent twisting moment will be the square root of m squared and t squared, right? So this is going to be square root of, what's m squared? M is, what's m again? 1 is 5, 1, okay, 3 and 10. Okay, so 3,000 squared plus 10,000 squared, right? So press your calculators, do that for me quickly. What do we have?
I've been at 10,440.
10,440. What's the unit? Newton.
0.30. Okay.
Newton.
10440.30, right?
Yes, sir.
0.30 Newton meter. Okay, Newton meter. All right. Now I will want this thing in Newton millimeter. Anyway, let's get to my calculation. So now, since I know this and I know this, I can now find my D. So please mute yourself. So now my D is going to be this guy, 16, the cube root of 16 times this guy, divided by pi is a number 3.142, and this one here is 83.3, right? And it is Newton per millimeter squared. So what we want to do to make this work is that this has to also be millimeters. Okay, so what do you do to this to make it to become millimeters? Quickly, what do you do to it to make it to become millimeters?
Divide by
1,000, sir.
Divide by
1,000.
1,000? No, sir. No, sir.
Times 10 raised to power 3.
Times 10 raised to power 3. So you are putting a milli. Milli is 10 to power 3. Okay, so you must add the 10 to power, milli is 10 to power minus 3. You must add the 10 to power 3 for both of those to cancel out. So effectively, this is times 10 raised to power 3. Great. And that's so that our diameter can be in what? In millimeters. So let's go. So what do we have? when you do all of that?
$86.101.
86.101. And the value?
102, sorry. 102.
102 approximately.
Approximately 102 millimeters. Great, right? Now that is us using the maximum shear stress theory, the Guest theory. Now, let's go and try out, because we need to know whether this value is bigger than the one if we had used the maximum normal stress theory. Now, the maximum normal stress theory, oh dear me. Using the Rankine's theory, okay, which says that the equivalent bending moments can be found by half of m plus the square root of m squared plus t squared, right? And this should equal what's it called? Pi divided by 32 times my sigma b, which is a maximum allowable sigma b I'm so fatigued, I'm not coordinated, times d cubed, right? So that's what we're looking for. You will quickly recognize that this guy alone is the same as this, our TE. It's TE, right? We found him before. So to ease our calculations, we can just express this whole guy as, we can express him as m plus t underscore e, right? That's simply what that guy is then. So again, our d will be the cube root of 32 times m underscore e, the equivalent of that, divided by pi, divided by pi times what? Sigma b, right? So again, we look at this equation. For us to find d, 32 is a number, pi is a number, we need to know me, okay? And me is half of this guy. Okay, we know TE already, so we add that and calculate, and then we need to find sigma b. So again, we just go ahead to say that our m underscore e is half of m plus TE, which will give us half of what is m? M was 3,000, right? 3,000 plus what was TE that we found? This guy here. So add those two guys, find the half of them, and give me what is ME. Quickly, 3,000, that will be 13,440 point that divided by 2. That will be 6. 6 what? My brain is not working this morning.
6,720.155.
6730.155, right?
6720.
2. Okay.
Yes, sir.
And this is in Newton meter. Okay. We can write this as 6720.155 times 10 raised power 3 in Newton millimeter. Okay, so that when we get our calculations, it's easier. And then we can find the maximum allowable shear stress by dividing the ultimate
No. You need to complete it one.
the ultimate shear stress by the factor of safety. Okay. What's the ultimate, I say shear, ultimate normal stress? What was the ultimate normal stress? Let's go back to what we're given. This is 700 megapascals, right? So somebody should quickly tell me the value of 700 divided by 6. What do we have?
116.67.
116.67 megapascals. Is that correct?
Yes. Yes, sir.
All right. So now we have all it takes to find the value of D. So we come here and say D, which is that equals this value is this guy. So copy and put him here. And this one is this guy. Put him there. Okay. So it's left for you to punch and tell me what that value is. D is. I hope that as we're doing this in class, you people find calculators and be following. Calculator skills is one thing. If you just sit and you're watching, say again.
83.72.
83.72 millimeters. So I was saying that you should be following, because as you calculate yourself, you build up conversance with these values and how to calculate them. If you just sit and you watch, and you enter the exam hall and that's the first time you are punching calculators, you will get confused. You will not know how to do cube root. You will not know what to multiply first and divide first before you do another one. So please get calculators. You will need calculators in the exam hall. Even though it's open book exam, borrowing of calculators is not allowed. So go and buy your own or borrow from somebody. As we're doing these classes, as somebody who is not doing this course, right? Be following us to calculate so that you can build your own confidence and skills in how you operate your calculator. Great. So based on these theories, the guest theory yields a larger diameter. Hence D equals, we go back and so we say when we do this two, we compare which of them is bigger. And obviously 86.102 is bigger than 83.72. So 86.102 is what is worked with. Therefore, what did the question ask us? It said that we should determine the diameter of the shaft. Therefore, the diameter of the shaft is selected to be what? What will be the value?
86.102 millimeters.
What's the standard? We're looking at standard shaft sizes. What's the standard shaft size above 86.02? 90, right?
Yes,
90.
sir.
So we'll select this to be 90 millimeters. All right. So that brings us to the end of this class today. Any questions? Any questions before I go? I'm going to send the slides to you guys so that you will go through. When we come next time, I will not be explaining, I will not spend time to explain how the equations were developed. I may just spend 1 minute to explain what is what in the equation, and then we'll go into examples so that we need to finish shaft quickly and get into bearings. Is that okay? There's a lot we need to do with bearings. Bearings is where you have to look at tables and all of that. You need to know where to pull up what value and all of that. So we need to hurry up with this and move on to bearings. So any questions? Any questions? It's a very long way to go. Okay, since there are no questions, I'm going to stop sharing my screen. And we can also stop recording now.